Hello, this is Fan from University of Tokyo. Today, I will introduce our work on decentralized attention-based personalized human mobility prediction. Imagine you want to go shopping, you drive your car and get stuck in the traffic jam. Maybe you will regret going shopping or driving the car. However, if you know the traffic jam in advance, you may change your mind, either go there on bicycle or simply stay at home. In this sense, in many application scenarios, instead of where the user is, where the user will go matters. Thus, to predict the future movement of a user is very important. It upgrades current location-based services to future location-based services. Now let's look at how future movement is predicted. Your smartphone with the GPS function can collect your daily trajectory and train a model for prediction. But most of the model requires a large training data set to achieve a good prediction accuracy. So conventionally, you upload your private data to the central server, and a more sophisticated model is trained there. However, user location private data is leaked. Nowadays, location privacy has drawn increasing attention. GDPR was published by EU law in 2018 to restrict the usage of personal data. And the latest iOS and Android system also enforces more restriction on location data usage. In this spirit, there are two challenges in this work. First is human trajectories differ significantly from one user to the other. The second is how to train a model use all users' data without seeing users' data. We proposed a meta-learning and federated learning methods to address these two challenges respectively. First, let's see how to make the predictor more personalized. For a conventional predictive model, given the most recent trajectories of a user X, shown as blue, we aim to predict his or her future movements as Y, shown in red. In this way, the predictive model is the same among all the users. Using the paradigm of meta-learning, we use each user's historical trajectories data as XU to configure the personalized predictor FU. Note that the model F is the same among all the users, but customized to FU with the help of different users' historical trajectories. We proposed an attention-based personalized human mobility predictor shown in this slide. The intuition of this model is to learn to retrieve the similar trajectories in the historical trajectories database that enhances our prediction. Because each user has its particular historical database, our predictor is personalized. In this example, we can see that given our most recent trajectories shown in blue, we can retrieve the useful information from past trajectories, especially brown and yellow one, and make a more accurate prediction. A quantitative evaluation also showing that our predictor is more capable in predicting the highly periodical behavior, like the commuting patterns in the morning and the evening rush hours, and the weekdays compared with weekends. Okay, let's move on to the second challenge. That is how to train a model that uses all the user's data without seeing users' data. Let's compare three different solutions to human mobility prediction. First, we use only local users' data without any communications with other users. In this case, the data we can use is very small, so we can hardly train a good predictor. In the middle, we can see a conventional centralized prediction. Every user uploads personal data to the central server. In this case, a stronger model can be trained, but the privacy is violated. On the right, we show how we do in this paper in a federated learning paradigm. We keep each user's data in local, unmoved, but train the model jointly by communicating with the model weights. Thus, we equivalently use all users' data to train the model, but the users does not need to upload their data to the server. In other words, we move the model rather than the data in the training process. So the federated learning paradigm is shown as when the user is using the smartphone, we collect the trajectories of the user in the background and store it in the user's smartphone. When the phone is idle and plugged in, this phone can join the federated learning cycles by synchronizing the model, making a small adjustments of the model to feed local data, and upload the model changes to the server. We also propose 3 different pre-training tricks to accelerate the training process, including pre-train from open data sites, pre-train from smaller data site, and which can be collected from volunteering users, and also pre-train from another city. As we can see from these figures, pre-training tricks can be effective in accelerating the training process, especially in the early stage. From our quantitative evaluation, we can see that our proposed model can not only achieve a similar accuracy with centralized learning, but also outperform baseline models from conventional human mobility prediction models. Thank you for listening.